All right, this is Physics 1101, Chapter 6 lecture on work and energy. All right? And this will be part of chapters 6, 7, and 8 for exam 3, which will come up later this month. And we'll go from there. So, we talked about forces. And again, we go back. Force is mass times acceleration. All right? And then we go back to the force. So if we apply a force, all right, say we got a 100 kilogram block, and we apply a force over a distance of 20 meters, right, of, say, 10 newtons, let's say 100 newtons, just to make it easy, right? Question asked sometimes is how fast is it going at the end, right? Now, if we apply a force of 100 newtons, the acceleration will be force over mass, which will be 100 over 100, which is 1 meter per second squared. So this is what we've had for chapters 3, 4, and 5, as far as that's concerned. And then to get the, so that's the acceleration. And then if we go back to chapter 2, we can figure out how fast it's going by using the expression v squared is v naught squared plus 2ax. Now in this case we start from 0. So it's going to be v squared is 2 times 1 times 20, which is 40. And then v is the square root of 40, or approximately 6.5 meters per second. So that's how fast it's going at the end. All right? So this is back from the earlier chapters. Now we're going to get into this concept of what we call work and energy. And as you realize, I mean, if this is a frictionless surface, right, you accelerate it to this amount, and then you let go of it, and it's going to slide at a speed of 6.5 meters per second, more or less, for all time. Right? You pull it for this long, let it go, and keep going. We're going to be doing a little bit different approach here in chapter 6, using the concept of potential energy and kinetic energy, which actually make it a little easier to work with as far as doing some problems here. So, okay. All right, so let's keep this problem here. All right, we have, for this particular problem, we got this is the answer. All right, so keep that in mind. So I have force is 100, mass is 100 kilograms, and V is 6.5 meters per second, and X is 20 meters. All right, so what we're going to be doing here, then, is doing a little bit different approach. And we call this concept of work, which there's a nice diagram in the book, is force times distance. Now you can see a pitcher throwing a ball. They apply a force to their arm. And how it goes, they want to pitch it as fast as possible. The way you do that is by applying a force over as long a distance as you can. All right? Same thing here. So picture when they have an arm, throw it, they don't just like go like that. They swing and go all the way through. So they apply a force over a much longer period of time, get the thing accelerated, and go from there. So we have the same thing here as we do then, is if you have a force, right? Now technically, for work is force times distance, right? Where F and X are both parallel. So they're in the same direction. Technically then, if it's pulling at an angle, so if you have a case like this, right? If we're pulling an angle, this is F, and this is where we're pulling it, and this is the angle, and the work is F times X, or D, as they use in the book, times the cosine of the angle between this and that. The force is pulling that way. This is what we have here. So we'll have this, cases like this. So let's do an example. We apply a force of 100 meters, 100 newtons, pull it for 20 meters at an angle of 30 degrees. So, all right, cosine of 30 degrees, that would be 2,000 times 0.866, which would be roughly 1,750 newtons, or 1,700 Newton meters, because it's newtons times meter, which is what we call the joule. All right, the unit of Newton times meter is a unit joule, or capital J. All right, named after James Joule, who first did work. So when we do these kind of problems, work will be measured in joules. And this is a unit of energy. All right, for most of our problems, we're going to have the force and distance will be in the same position. So you can see if it's parallel, it's maximum, but if it's 90 degrees, the force is doing no work to pull it that way, so the work would be zero. All right, so if the force and the distance are perpendicular to each other, the work done is zero. All right, so let's look at this particular problem. All right, so the work for this problem before is force times distance, x, 100 newtons times 20 meters is 2,000 joules. So this is the work we do on this. Now we accelerate it up to a certain speed, and then it just goes on at that speed. This then is part of section 6.3, and what we have here then is the work done leads to kinetic energy, KE, which is given by 1/2 mv squared. All right, so the kinetic energy of an object of mass m and speed v is given by this in units of joules. So what we're going to have here is this is the work given to it. This then becomes the kinetic energy this object has. So it has 2,000 joules to it of kinetic energy. All right, so I'll let that sink in here. So we got kinetic energy as far as we've done. We've done work on it, got it up to a certain speed, it's on a frictionless table. Now it has this kinetic energy, which, you know, as see, can be rather dangerous because the kinetic energy goes as the square of the speed. So you double the speed, you're going to quadruple the amount of energy you have. All right, so back to our problem here. If we do this way, as opposed to what we've done before, we could ask how fast is this thing actually going? So it's been given 2,000 joules of energy. So that's kinetic energy is 2,000 equals 1/2 mv squared. So multiply both sides by 2, divide by 100, and we end up with 40 is v squared, and so the square root of that gets us 6.5 meters per second. Lo and behold, it's the same answer as we had the first time. All right. So we're doing this using an energy principle. Right? We did it before using forces and the acceleration and the equations for velocity based on acceleration and mass. This time we're just given the force, how far we accelerated for, and from there we can solve the speed it's going. So this is our expression for kinetic energy. All right? Okay, so it's proportional to the force times the distance. So this is where we have the work done gives us kinetic energy. So the work, which is 2,000 joules, results in kinetic energy, which is 2,000 joules, and we can calculate the speed that this thing is going when it's let go. All right. So that's that section. All right, the next section, which I will cover, is on we call potential. So let's keep this up. We'll rewrite that. Okay, so you have kinetic energy is 1/2 mv squared. All right. So that's kinetic energy. Potential energy, so, is potential energy. And the easiest one is gravity. All right? If we have an object at a certain height, y, and drop it, it has potential energy up here. So this is the surface, say it's y is 10 meters. It's about 30 feet, 3 floors. It will have potential energy given by mgy. Where for most of these problems, g is 9.8. So we're going to be dealing with positives. So we're going to take the positives, 9.8 meters per second squared, which I will use 10 meters per second squared for the problems I'll be doing, just so I can avoid a lot of decibels and stuff. All right? So potential energy, gravitational potential, you lift something up, because when you let go of it, it will have this potential energy, and say the mass is 10 kilograms. This is the potential energy up here will be mgy, which will be 10 times 10 times 10, which is 1,000 joules, right? So it's potential energy up here. When I let go of it, it has a constant force of mg. So this is the weight, this force, mg times y. This is the work done on it. This is exactly what we've had before. So mg is the force, y is how far it's pulled or falls. At the bottom, just before it hits, it will have kinetic energy of 1,000 joules, just before it hits the ground. So this potential energy converts to kinetic energy. And this is an example we call conserved energy. And in this case, what we have is we can come up with a concept called the total energy, which is potential plus kinetic is a constant. All right? So we have here, and this we can see with the lab, we have the lab on kinetic energy, as we have a falling object, all right? We plot potential energy versus height. and kinetic energy versus height. Well, you can see if we start at a certain height, it will fall down and go to 0, and the kinetic energy will go up, so that the total energy, TE, stays constant, right? So the total energy stays constant all around. So this plus this is a constant when we have energy is conserved. Now that's not always going to be the case, but for most of the problems we'll be dealing with, that's true. If you drop something, it gains kinetic energy. And again, we're going to be dealing with just before it's the bottom. Or if you had the case of, say, a super ball that drops, hits the ground, bounces back up to the same height, and keeps going back and forth, that's another case of that. But it has to be something where it falls and loses no energy into the ground. If you drop like something else, let's say this, all right, it's just, there's no rebound, it just stops. So this is what we have, energy is conserved. So based on that, we can figure out how fast this thing is going at the bottom. All right, kinetic energy at the top is 1,000 joules. Potential energy at the top is 1,000. Kinetic energy at the bottom is 1,000 joules. And the total, so as this goes down, this goes up, so the total remains constant until just before it hits the ground. So we can then figure out how fast this thing is going just before it hits the ground in the same way, in a little different way than we did before, we'll get the same answer. So we have here, I'll leave this. This is our potential energy. Kinetic energy is given by 1/2 mv squared, which in this case 1,000. And the mass is 10 kilograms, so it'll be 1/2 times 10 v squared. So multiply by 2, so it's 2,000 over 10, which is v squared. 200 is v squared, so square root of 200, which is roughly 14 meters per second. Okay, so it'll be roughly going, you drop it from 10 meters high, which is about 3 floors, it'll be going roughly 14 meters per second, or a little bit over 30 miles an hour when it hits the ground. Okay. You're going to be using this when we do the ballistic pendulum lab, lab 7, which I'll get into later. You know, you can see the video on that. But that'll be the same kind of concept of momentum and collisions, but that'll be part of chapter 7. I'll talk about that as far as that concept is concerned. And we'll get into that. Okay. Anyway, so, so we have a conservative force here, meaning there's no energy lost. If it's non-conservative, so if you have friction involved, or if it hits the ground, then that's what we call non-conservative force, and things are different. So, this is our expression. Potential energy plus kinetic energy is a constant, and potential energy of gravity is that, and this is potential energy, kinetic energy in all cases. All right, we're going to do another case here, and this will be for a spring. Okay. And so this is the other example we'll be using. And what do we have here? And we'll leave that up. And the example here is like if you have a toy gun. Okay. All right, you take a toy gun, push it in a certain distance X. It will have potential energy stored in there, And then when you fire it, it will go flying out. All right. So I'm going to look at this example here. We'll do this in K. In other words, we'll do a different type of thing. So this will be an example of a spring, which let's look at something here. So you can look at this example here of a spring, right? So if I can find a little ball quick. Not. Doesn't matter, we'll use this. Oh, here's something that'll work. This will stay. Okay. So I have a spring. You compress it at a certain distance x. Okay, a spring it takes a certain amount of force to push this. Right? And the force that is on the spring is not like gravity. For gravity, it's just mg times, so this is a constant force times distance. For a spring, when you compress it a certain amount of distance, right, x, the force on it goes as k times x, where this is what we call the spring constant. So it's not constant, but the force, as you have ever experienced, gets harder and harder and harder the more you try to compress it. So this spring constant is in units of Newton per meter. So if we do gravity, right, force y, it stays constant, right? The force makes no difference. Force is constant all the way down. For a spring, the force actually goes as proportional, where the slope is k. So this is how a spring is somewhat different from that. So the spring goes as Fkx, and what this means then is if we compress it like we do in the handout, so we compress this a certain amount, right? And I'm not going to worry about being precise about it. Okay, it takes force to hold it down. Now when I let it go, all right, it goes, that potential energy gets converted to kinetic, pushes it out, converts to kinetic energy, which then causes it to rise a certain height and then come back down. So it's a little bit complicated problem. So the force is given by that. So the potential energy, so this is gravity. For a spring, the potential energy is going to be given as 1/2 k x squared, where k is the spring constant, and x is how far you've compressed it. So in this case, I compress it this much, say 10 centimeters, all right? It converts it, when I let go, it flies up and goes up in the air a certain height. So we have a spring. Well, we can just do the example right here. All right, I'll show you this one right here. We have it compressed a certain amount. Okay, you compress it, you let it fly. That gives it kinetic energy. So we got potential energy, converts to kinetic energy, which converts to potential energy. So, at this point, this is where we have potential energy. Now, let's just do a simple example here. So we'll use K. K is 100, let's see, Newton meters. I want that. Let's say K is 1,000 newtons per meter. Because that would mean to press it 1,000, it would be a lot of force, the whole meter. I'm only doing it a few centimeters. It's probably, 5 centimeters. So X is 5 centimeters, which is 0.05 meters. Then the potential energy, when I first compress this, is going to be 1/2 kx squared. And again, I'm just making this problem up. So it'll be 1/2 times 1,000 times 0.05 squared. And I'm going to need to get a calculator. That will be, okay. Gives me 1.25 joules, right? Which isn't a whole lot. Yep. All right, now this thing, trying to guess how much it weighs. Maybe a quarter, half a kilogram. I don't think it weighs a pound. Might be. Yeah, let's say it weighs this probably weighs mass. So this thing probably weighs mass of 100 grams. Which is 0.1 kilograms. Okay? So again, I'm doing this real example. And I can estimate, again, I'm taking, I want you to see how close. All right, it goes up about this high, which is roughly 60 centimeters. So rise is a height of 60 centimeters, y, which is 0.6 meters. So we compress this. Okay, move this out of the way. Compress, we have this spring. We compress it from 5 centimeters. We let it extend out. Where again, this is X is 5 centimeters. It goes out with a kinetic energy given by 1/2 mv squared. And then the ball will rise up to a height y of 60 centimeters. So we start with potential energy, 1/2 kx squared, which converts to kinetic energy, which converts to potential energy of gravity, mgy. And we can see how accurate we are. Again, I'm just kind of making this problem up. Is it reasonable? All right? So all these cases, we go from potential, kinetic, to potential. So unlike the gravity problem where we just drop it, let it fall, we've added another part of energy in here. Okay, so, all right, and again, it's on page 154 in the textbook, but I've also shown you. I'll show you one more time, just so in case you get a sense of what we're actually looking at. So we're starting from right, C, going back to B, back to A. Okay, and see how high it rises. All right, so let's clean this up a little bit. All right. So the potential energy of the spring is 1.25 joules. Then that converts to potential energy of 1/2 kx squared is 1.25 joules. That converts to kinetic energy, just before it flies up, of 1/2 mv squared, which is also 1.25 joules. And in this case, we only want to see how high it goes up. Well, that equals the potential energy of gravity, which is mgy, or mgy, which is also 1.25 joules. All right, so we can figure out how it goes. Again, we're going to use G is 10 meters per second squared. M is 0.1 kilograms. So we're going to end up with is PE, which is 0.1 times 10, which is convenient, times Y, which is 1.25 joules. And we end up with Y is about 1.25 meters high. And for a made-up problem, G is, I see. G is 0.2, 200 kilograms, 0.2 kilograms. Then this will be 0.2, sorry. So we're saying this is a 200 gram weight. It's roughly the same weight as this. So we're going to be, so the mass is 200 grams, 0.2 kilograms. So then this will be 2y is 1.25 joules. So y will be approximately 0.63 meters, or about 63 centimeters, which is actually very close to what I actually had. So what we have here is we have potential energy by compressing this, right? When I let go, it sends it flying up. It then goes up a height of about 60 centimeters, which is pretty close to what we actually have here. So we have potential energy of the spring, which converts to kinetic energy of the ball, which converts to kinetic energy, potential energy of the spring. So it could potentially, if we have this exactly right, come down, press here, compress it, and start the whole process all over again. So this is the concept of conservation of energy in a somewhat more complicated problem. So potential energy of gravity is given by this, potential energy of the spring is given by that, and all these convert to kinetic energy. All right, so that's what we have here, and all this is based on the fact that in a conserved system, total energy is potential plus kinetic is a constant. All right? So, all right. So, that's what we have there. 6.8 talks about other types of energy as far as that's concerned. All right. The last thing I'm going to do, so this is all energy. Last thing I'll talk about is power, which is section 610. Roughly talk about that. All right? So this will be all chapter 6. Okay? So the last part is 610, which is power. And power is in units that we call watts, named after James Watts, or W. Right? Power, a light bulb runs at 100 watts. Power is how much generated per second. Energy per second. So power, which is P, is given as work over time. So how fast you do the work is what matters. All right? So an example be here. I mean, they got a picture here of somebody climbing the stairs. All right? Or some other case. All right? So say you climb. You weigh 100 kilograms. All right? Your mass. And G is 10 meters per second squared. And you climb, climb up 30 meters is how high you are. All right, the work you do will be mg times y, which would be 100 times 10 times 30, which is 30,000 joules. All right? 30,000 joules of work. So 30 meters is roughly 100 feet, or about 10 floors. All right? Now, if you do it slowly, so you walk up, so you take very slowly, and for 10 floors, say it takes you 5 minutes to do it. All right? Say the time, 5 minutes, which is roughly 300 seconds. All right? Then the power you're going to do will be the work over the time, which would be 30,000 over 300, which would be, 100 watts. Okay? 100 watts of power. Now, suppose instead of walking slowly up, you do 10 floors, and you do it in, 10 floors. If you do it really fast, say you do it in 1 minute. 1 minute, it's just roughly 60 seconds. Then the work done, in that case, will be, so here's 300 seconds for here. For this case, the work over the time will be 30,000, still the same amount of work, over 60, which will be 500 watts, which is actually a very large amount of power. So this would be racing up the stairs. This would be doing 10 flights of roughly a flight every 6 seconds, which is possible for somebody who's really fit. So this is the work done. The energy you do is the same in both cases, but the power is much greater for each one. This also goes back to the idea of when you run, how much energy do you burn? Really doesn't matter how fast you go. If you do, say, 5 miles, if you do it slow or if you do it quick, if you do it slow, you're spending more energy, but you're taking over a longer period of time. You're putting out more wattage, less wattage, more longer period of time. The energy is still the same, but with the distance. So this is the unit of power, concept of power, which is work over time. And the units are watts, right? Which is a joule per second. And that is chapter 6. And there you go from there. Okay, so have a good day. Let me know if you have any questions. This will be related to a couple of products.